My name is David Hardy. As lead developer of the NAMD Molecular Dynamics program, I am grateful for the opportunity to tell you about the work that the development team has been doing to port NAMD to SYCL. This work matters because molecular dynamics combats diseases like COVID-19. MD simulation software and HPC resources together provide access to spatial and temporal scales not available to physical experiments, providing a scientist with a computational microscope to show the atomistic dynamics that can reveal the molecular basis for diseases. By studying viruses and other diseases with MD and related methods, researchers can inform the development of new treatments and therapies. An example of the scientific studies enabled by NAMD is shown on the right. This large collaborative project led by the Amaro Lab at UCSD constructed an all-atom model of the Delta variant of the SARS-CoV-2 coronavirus suspended in an aerosol droplet, also modeling the molecular environment formed when an infected person exhales. This study, selected as a Gordon Bell Special Prize finalist at SC21, not only demonstrated the stability of the coronavirus in aerosol droplets, but also advanced the state of modeling these types of systems. On the computational side, the simulation included over 1 billion atoms, among the largest such biomolecular simulations ever performed by NAMD or any other software. The simulation was scaled up to 4,096 nodes of the Summit supercomputer at the Oak Ridge National Laboratory, where each node contains 6 NVIDIA V100 GPUs for a total of over 24,000 GPUs used in parallel. This movie of the coronavirus spike opening shows a dramatic example of the structural changes that can be seen by molecular dynamics. Understanding the dynamics of the spike protein complex is important because this is the first point of contact leading to infection of a cell. The glycan shielding allows the virus to remain unrecognized by the immune system. As the spike opens, it is able to attack a cell, and the more it opens, the more infectious it becomes. These studies are providing scientific evidence of why the Delta variant is more easily transmitted than the original. The NAMD team also collaborated last year on another project that was also a Gordon Bell Special Prize finalist at SC21, studying the replication transcription complex, which is a multi-domain protein responsible for replicating and transcribing the viral mRNA inside a human cell. Attacking this function with pharmaceutical compounds is a pathway to treating COVID-19. The systems simulated here were much smaller, in the range of 1 to 2 million atoms, and were able to make good use of our GPU-resident version of NAMD on the Theta GPU cluster of DGX-A100 nodes at Argonne National Laboratory. Performance scaling plots for MD, like the one seen on the right, show performance measured in the number of simulated nanoseconds per day of computation. The plot shows the strong scaling of the 1.1 million atom RTC system running on up to all 8 GPUs of a DGX-A100. It's interesting to note that for this particular system, we match the performance of 128 nodes of the TAC Frontera supercomputer, simulating at 47 nanoseconds per day while using just 3 GPUs. So now I'll transition away from telling you about projects we've done with NAMD and instead tell you more about what NAMD is and provide you with enough background that you understand how we are using GPUs in NAMD. NAMD is now a more than 25-year-old molecular dynamics application written in C++ with Charm++ parallel objects. NAMD simulates the movements of biomolecules over time with an emphasis on the parallel scaling of large systems. And although we have over 25,000 registered users, an even better measure of our impact on the biomedical community is that our reference papers have received over 16,000 citations, with a growing number of citations each year. And now to introduce what we are calculating. At its most fundamental level, a molecular dynamics simulation performs a numerical integration of Newton's equations of motion. The atoms are represented by their position coordinates, and the forces between atoms are defined as the negative gradient of a scalar potential energy function of the positions. For biomolecules, this energy function consists of bonded terms that take into account the covalent bonding between nearby atoms, and also non-bonded terms between all pairs of atoms that include the van der Waals forces and the electrostatics forces that model the atoms as point charges. In practice, we might integrate a given system for millions of time steps in an effort to achieve biologically relevant timescales. Most of the computational effort for each time step is the calculation of the forces, and the most computationally intensive part of the force calculation is for the non-bonded forces. The time steps must be calculated in sequence, which limits the parallelism for an MD simulation to the calculation performed within each step. Diagramming the computational workflow, we start by initializing the particle positions, then use those positions to calculate forces, and use the forces to update the positions. This process loops for millions of time steps. Occasionally, we will output reduced quantities used to monitor the state of the simulation, and sometimes position coordinates to record a snapshot of the trajectory. These movies I have shown are taken directly from the trajectory output of simulations. Within this time step loop, the force calculation requires the majority of computational effort and can be as much as 99% of the overall computational work, with the rest being the positions update. Now, it's common for parallel programs to decompose over the data elements being calculated. NAMD does do this using a spatial domain decomposition of atoms into equal volume patches. When calculating range-limited pairwise forces between atoms, we treat these as interactions between neighboring patches. NAMD goes further by also decomposing over these patch-patch interactions, referred to as compute objects. Considering the bottom right diagram and thinking about it in 3 dimensions, this gives us 14 purple diamonds representing the compute objects for every blue square patch, providing a much larger set of elements to parallelize over than just the patches themselves. As the atom positions are updated, we have to update the domain decomposition by migrating atoms between adjacent patches. In NAMD, we are able to load balance by migrating the compute objects to keep processors more consistently occupied but not overloaded. Now let's look at how the NAMD parallel workflow incorporates GPUs. Consider the patches having been distributed across a parallel computer. Each patch starts with its set of positions, which must be sent to the compute objects using a multicast communication operation, since some positions might go to different compute objects, and a compute object might receive positions from different patches. The compute objects perform their work in parallel. Then the forces are received back to the patches through a reduction communication operation, since a force can receive partial contributions from multiple compute objects. This part of the force computation is done in parallel with the particle mesh AWOLD, or PME, calculation of long-range electrostatics. PME uses point-to-point communication with patches to perform a distributed forward 3D FFT into reciprocal space, followed by a summation in reciprocal space and a backward 3D FFT back into real space. GPUs can be engaged using an offload strategy to perform the scalable parts of the force calculation. In order to use a GPU, you need enough work to make it cost-effective to transfer data to it and launch a kernel, which requires aggregating the compute objects, which effectively is aggregating atom positions. GPUs were first introduced for the short-range non-bonded force computes, the most flop-intensive part of the entire force calculation, and later for the bonded computes and the scalable parts of the PME algorithm, as it became necessary to offload more work from the CPUs. The original GPU offload scheme provided a partitioning of work between CPU and GPU, eventually with all parts of the force calculation on the GPU and the coordinate updates on the CPU. The idea with this strategy was to overlap the CPU work with the GPU work. As we progressively offloaded these force calculations to the GPU, it's not that the speed up for calculating each small contribution on the GPU was that significant, rather that we benefited from removing work from the CPU. The GPU offload approach worked quite well on earlier GPUs when we were able to get good overlap between the CPU and GPU workloads. However, once we get to the Volta generation and beyond, profiling shows the GPU offload approach to be CPU bound. Using Insight systems with NVTX tags to trace execution of the CPU kernels showed us that the big gaps in the timeline between the GPU force calculations were due to the GPU waiting on the CPU to finish its integration calculations. To better utilize modern GPUs, we developed a new GPU residence scheme in which we move the integrator to the GPU and maintain data on the GPU between time steps. Now, instead of integrating the atom positions on the CPU, aggregating the position data and copying to the GPU, calculating the forces on the GPU, and streaming the results back to the CPU to continue the next integration step, we now integrate the atom positions on the GPU, calculate the forces, and repeat. Due to a change in the data layout needed between the integration and force calculation kernels, some extra kernels were needed to fill the position buffers at the force kernels, then fetch the force buffers and convert the force back to a structure of arrays form for the next integration step. Profiling this new GPU resonance scheme shows that the GPU is fully utilized with no more CPU bottleneck. It's also interesting to note the difference in CPU utilization between the two approaches. The CPU activity appearing in black shows how busy the CPU is kept for the GPU offload version due to continual polling for results back from the GPU. By contrast, for the GPU resident version, the CPU is used primarily for managing the GPU kernels, so is not kept continually busy. Benchmarking shows that the GPU resident scheme on a single A100 GPU is much faster than the GPU offload version over a range of problem sizes. The GPU resident version is more than twice as fast as the GPU offload version for problem sizes in the range of 90,000 up through around 300,000 atoms. The sweet spot for best performance improvement seems to be around 100,000 atoms. Clearly, NAMD has done a lot to leverage CUDA. So why are we interested in adopting SYCL? We were first motivated by needing to support NAMD on the upcoming Argonne National Laboratory Aurora supercomputer, which is to be one of the first US exascale supercomputers and will be based on Intel GPUs. However, SYCL provides several additional advantages. It provides a modern C++ interface to GPU devices with host-side code that is much simpler than OpenCL. You can define the same data structures, definitions for both host and device using a single source and single compiler for host and device code. And most importantly, it provides a vendor-neutral language and library solution for leveraging GPU devices. Although SYCL and CUDA target similar hardware, they have some differences in perspective. Some of the differences are due to SYCL's use of modern C++, in which kernels are defined as unnamed lambda expressions and error handling is done with try-catch blocks. Other differences arise as design decisions in SYCL and OpenCL. The SYCL work queue is analogous to a CUDA stream, but it defaults to out-of-order execution. You must specify accessor functions to enable SYCL kernels to access device buffers. SYCL also supports a flexible vector width to produce performance portability across different hardware. We had three main design decisions for porting NAMD. The first was to extend NAMD without disrupting its current GPU support, which we achieved by using preprocessor switches to isolate the DPC++ extensions from existing code. The second was to leverage existing GPU kernels and data structures rather than rewrite them, which we achieved by translating CUDA kernels to DPC++ and copying supporting data structures and kernel management infrastructure into DPC++ versions. The third was to add support incrementally, guided by Amdahl's law, to accelerate the most computationally expensive parts first. For this, we began by porting the short-range non-bonded force kernels and continuing with the PME and bonded force kernels. Doing this effectively mirrored the order of our original CUDA development. NAMD has a lot of CUDA code. We eventually want to develop SYCL support for everything, including our recent GPU resident version. However, it made sense to start porting from a stable codebase with the GPU-Offload version. Note that the GPU-resident version depends on the force kernels from the GPU-Offload version, which alone requires porting around 20,000 lines of code. The overall porting strategy employed a divide and conquer strategy using preprocessor switches to decouple components in the CUDA code, which significantly reduces development and debugging complexity. The separated components consisted of the short-range non-bonded force kernels plus the device utilities, which were about 7,500 lines of code. The bonded kernels, which were around 4,000 lines of code, and two versions of PME, one for scalable parallelism and the other for fast single-node simulation, together almost 7,500 lines of code. We also need supplemental libraries from Intel's One API. The 1DPL for C++17 parallel STL operations, including reduce, shuffle, atomic ref, sort, and scan, which replaces the cub library calls for CUDA, and the 1MKL FFT, which replaces the CUFT library. We were able to get faster porting with the code conversion tool, utilizing Intel's DPC++ compatibility tool to convert the CUDA kernels into DPC++. This saves a lot of code porting effort by translating a number of CUDA idioms. We note that it also provides programmers new to SYCL a good guide to practice its syntax. In spite of having a code conversion tool, there were still a number of considerations beyond what any automatic tool is capable. For NAMD, we created new DPCPP prefixed versions of the relevant files in which we renamed object classes from CUDA to DPCPP. We also had to change certain fundamental data types. For example, CUDA float 4 had to become SYCL float 4. The use of CUDA warp level intrinsics in the short-range non-bonded force kernels required SYCL subgroups using reduce, shuffle, and atomic ref operations. The CUDA version makes use of the special texture memory for looking up force parameters. The texture memory unit has special hardware to perform linear interpolation from a lookup table, which we use for calculating force and energy values. To convert this to SYCL, we have to read values from global memory and explicitly perform the linear interpolation. We note that the non-bonded kernel calculates in single precision, while the later summation of tensor virial and scalar potential energy uses double precision. For bonded force and PME kernels, we again created new DPCPP prefixed versions of files and classes. The CUDA implementation maintains a bit flag for the 5 different bond force types, indicating whether GPU or CPU is used to calculate. This separation made testing and debugging easier. As I already mentioned, PME has 2 GPU code paths, one for single node and the other for multi-node. The CUDA kernels themselves were relatively straightforward to convert to SYCL. However, the single node version required extra work to replace CUFT with 1MKL FFT due to the fact that it does not provide an FFTW compatible interface. For this, we needed to account for the data buffer strides for real to complex forward FFT and pad the input grid to the SIMD vector length with the output from the backward FFT similarly padded. In order to avoid modifying the surrounding code, we needed to introduce additional data buffering kernels. Porting large applications from CUDA to SYCL can lead to a lot of debugging challenges, especially when dealing with large irregular arrays of structures. Large arrays may be pipelined through multiple kernels, which can cause code crashes at later stages when numbers become far from their expected value, for example, when NANDs appear. Sometimes we are even faced with porting a complex application outside of our domain of expertise. To address these debugging challenges, we created an array debug utility. Note that code porting mostly involves changing the syntax and library calls. Almost all of the algorithms and results remain the same, and most host-side code remains intact. We added a utility to capture device kernel buffers across different languages, in this case CUDA and SYCL. Buffers from the reference language are written to a file before and after each kernel call. Then the development language implementation reads the reference data files, comparing its kernel buffers against an expected result. This array debug utility provides easy-to-add macros around kernel calls and determines the earliest code location and element index for differences between device kernel buffers. The team has successfully ported the GPU-Offload kernels to SYCL. However, we presently lack meaningful performance results. The Intel GPU performance is not meaningful until we can access the XE-HPC Ponte Vecchio GPUs, which will provide important features for us, like double precision atomics. We had hoped to make use of the DPC++ compiler from CodePlay to compare performance on NVIDIA GPUs. However, their compiler does not provide 1DPL or 1MKL FFT libraries. What we have done is determine correctness through short trajectory runs. Even though an MD simulation at constant energy is in theory deterministic, it turns out that long trajectories will diverge due to non-determinism of the order of operation of parallel calculation and the non-associativity of floating point addition. This is simply due to the underlying nature of Hamiltonian systems and their solutions. What we can do is run an MD trajectory at constant energy for up to 500 steps, comparing total energy values with a known reference run. We use this approach to test DPC++ compilation of the SYCL port on two different sized systems that are representative of the size range of systems suitable for simulating on a single modern GPU. We run on three different DPC++ targets, showing that the relative error is within tolerance comparable to CUDA GPU simulation. The CPU-only run shows lower relative error due to its double precision calculation, as compared to the GPU device runs that are using mixed precision calculation. Our future work includes porting the GPU resident version of NAMD. Once Intel Ponte Vecchio GPUs are made available, we will need to optimize the GPU resident version for single-node runs and also optimize the GPU-Offload version for multi-node runs on Aurora's Cray Slingshot network. Other work that might prove interesting is to improve support for mainstream commodity GPUs, transforming double precision reduction into two single precision values using K-Han summation or compensated summation algorithm to preserve the low-order bits. Finally, long-term maintenance of multiple code paths is problematic, so it will be important to merge the SYCL and CUDA versions into a unified GPU code path. These code paths have many similarities, especially at the kernel management level. Even many aspects of these code paths at the kernel level are syntactic and could be unified to a strong degree. There are many people to acknowledge in the development of NAMD. Most importantly, I would like to acknowledge the SYCL DPC++ porting efforts of Tarek Mallis, who was our major code collaborator from Intel. We are funded in part by Intel through the One API Center of Excellence established with UIUC, and our primary source of funding is through NIH. Thanks for listening to my presentation.